Welcome to cloud security. When you upload data to AWS, you generally choose between two protective paths. You can use server-side encryption, where Amazon scrambles your file upon receipt, or client-side encryption, where you lock the data on your local machine before locking it into an AWS server farm. Despite the difference in exactly where that encryption happens, both of these AWS methods rely on the exact same underlying mathematical algorithm, the Advanced Encryption Standard, or AES. To understand AES, we start with the secret key encryption model. Sender A wants to communicate with receiver B. Both parties must possess a shared secret key before communication begins, turning a readable message into scrambled characters. Cryptographers define this environment as a 5-tuple cryptosystem. It consists of the plain text space for the clear messages, the ciphertext space for the scrambled output, the key space containing all possible keys, and the mathematical rules that govern the encryption and decryption algorithms. These modern algorithms are built entirely on two ancient cryptographic principles. The first is substitution, where you replace one character with another. The second is permutation, where you physically swap the positions of the characters. This source image shows the mathematical weakness of early substitution methods like the Caesar cipher. Notice that the total number of key possibilities is strictly limited to m factorial permutations. Because that key space is so small, a modern computer can test every single possibility and crack the cipher in a fraction of a second. To secure modern cloud infrastructure against those rapid computational attacks, we needed an algorithm that applies those ancient principles of substitution and permutation on a massive, mathematically complex scale. By the late 1990s, the old cryptographic standard, known as the Data Encryption Standard, or DES, was failing. Its 56-bit key size was no longer sufficient to defend against increasingly fast computer processors. In 1997, NIST, the National Institute of Standards and Technology, called for a replacement. They reviewed 15 candidate algorithms in 1998, narrowed it down to 5 finalists in 1999, and finally selected an algorithm named Rindell in the year 2000. Rindell operates as a block cipher. Instead of encrypting bit by bit, it processes data all at once in rigid 128-bit chunks. To fix old vulnerabilities, AES scaled up, processing those 128-bit blocks using massive 256-bit keys. By combining the block cipher structure with a massive key space, AES creates a mathematical lock so complex that brute force guessing attacks by modern computers are no longer a viable threat. To understand exactly how it works under the hood, we can look at Simplified AES, an educational model that scales the system down to a 16-bit data block. Key expansion splits and swaps the key through an XOR operation, generating distinct subkeys. Next, add round key mathematically XORs the plaintext with a subkey. Substitute nibbles uses S boxes to replace 4-bit chunks. Finally, shift rows swaps positions, and mix columns mathematically blends the data. Each individual round aggressively scrambles the data. Through repeated, layered cycles of substitution and permutation, the original message is obscured into noise. But this raises a technical question. How does the computer perform intense matrix multiplication during the mix-column step without the resulting numbers overflowing the strict memory limits of a 16-bit block? The solution relies on Galois fields, a finite field of modular arithmetic where numbers wrap around a fixed boundary. Addition executes as XOR logic. Multiplication uses polynomials. To prevent overflow, the system divides results against a fixed polynomial. The remainder keeps the data perfectly sized. This specialized polynomial math acts as the invisible engine for AES. It guarantees that the complex mixing happens instantly and cleanly within the strict boundaries of the data block. Reviewing the sequence, the goal is to turn a plain text message into ciphertext using a block cipher powered by the finite mathematics of Galois fields. Despite the polynomial division and XOR logic gates, AES is a modern, computationally sophisticated execution of Caesar's original principles of substitution and permutation. The layering of generated subkeys and the repeated cycling of substitution and permutation rounds creates a cryptographic barrier that modern computing hardware cannot penetrate through brute force. This brings us right back to the cloud. Whether you choose client-side encryption on your local machine or server-side encryption directly on AWS, this exact mathematical gauntlet is what activates to protect your files. AES provides the algorithmic verification that ensures every file stored or sent via the cloud remains exclusively accessible to those holding the shared secret key.